Hey, what's going on, guys? In this video we are going to see an example of non-inverting summing amplifier. In this particular problem we are going to see how to express this Vout voltage in terms of input voltages. Now this is a non-inverting summing amplifier because the input voltage is connected to the non-inverting terminal. In other words, we can say this is connected to the positive terminal. Positive terminal is non-inverting terminal. Okay, so this is a non-inverting summing amplifier. Now here, to create the equation, first we can deal with the bottom part, and when we deal with amplifier we have to know two things. We have to know that voltage across the positive terminal is always equal to voltage across the negative terminal, we can say approximately, and also the current entering or exiting this positive negative terminal is almost zero. Okay, so these are the two assumptions we have to make before we approach this problem. Now let's go ahead and do this. Let's deal with the bottom part. Here we have IF and this is II, and the current entering or exiting this negative terminal is 0. So all the current entering here, this node should be exiting through this one, because if this is 0, then all the current entering this node should be exiting through this one. And if we apply KCL at B, we can say IF is equal to II. Okay, and IF is, since the current is going in this direction, this is voltage out, right? V out, and V output, that's the voltage right here. So V out minus VB divided by the resistance in between, that is RF. So we can say this is V out minus VB divided by the resistance in between, that is RF. That is equivalent to II. II is VB minus 0 because this is connected to the ground, and the resistance in between is RI. Okay, now we are trying to find VO, so let's rearrange this equation. Let's bring this RF to this side. So this is going to become VO minus VB is equal to VB over, or VB multiplied by RF over RI. And also we can bring this VB to this side, and that's going to make this one VB times RF over RI plus VB. Okay, this one is VB, and here we can take VB common. If we take VB common, this is going to be RF over RI plus 1. Okay, so this is the equation we derived from this KCL at B. And let's look at the top part. Here we know that current entering this positive terminal is equal to 0. If this is 0, and if we apply Kirchhoff's current law at this node right here, we know the Kirchhoff's current law can be stated in two ways. Like we can say whatever the current entering the nodes should be equal to exiting the node, or we can say addition of all the current is equal to 0. So let's say addition of all the current is equal to 0. So here we know that we have three currents, I1, I2, I3. So addition of all the currents is going to be equal to 0. I1 plus I2 plus I3 is equal to 0. So if this is equal to 0, then we can write this one in terms of voltage and resistance. At this point we have V1 minus, at this point we have VA, because this voltage is going to be right here, same right, because we don't have anything in between. So the same voltage we are going to have right here. So this is going to be V1 minus VA divided by the resistance in between, that's R1, plus V2 minus VA divided by the resistance in between, plus V3 minus VA divided by the resistance in between, that is R3, is equal to 0. Now here we are trying to find, also we know that VA is equal to VB, because we know that voltage across the positive terminal is equal to voltage across the negative terminal. So let's write this one right here. Let's write this one with a different color. VA is equal to VB. So if we find out VA, we can express our voltage output in terms of input voltages. That's our purpose. Now let's try to find out VA from this one. Okay, so for this one, what I'm going to do is I'm going to separate all the VA, because if we find VA, that's going to be the VB, then we can rewrite this V out voltage in terms of input voltages. Now let's separate VAs. So this one can be written as V1 over R1 minus VA over R1 plus V2 over R2 minus VA over R2 plus V3 over R3 minus VA over R3, all of them are equal to 0. And then we can move this VA and all the VA to the other side of the equation, or we can say let's combine this V1, V2, V3 together. So this is going to be V1 over R1 plus V2 over R2 and V3 over R3. All of them are positive because if you look at the sign in front of this V1, V2, V3, all of them are positive. So that's why we have this one right here. And in the other side we can take the VA common, and all of them are negative. If I move this one to the other side, that's going to be positive. So this is going to be 1 over R1 plus 1 over R2 plus 1 over R3. Here you can see this is addition of all the parallel resistance. So the equivalent resistance can be replaced with 1 over RT, right? So we can replace this, all of this, with 1 over RT. Okay, let's write this one with a different color. So this is V1 over R1 plus V2 over R2 plus V3 over R3. That's equal to VA times 1 over RT. This is equivalent resistance. Now what I'm going to do is I'm going to bring this RT to this side because our purpose is to find VA. Okay, let's bring this RT to this side. So that's going to become VA is equal to RT times V1 over R1 plus V2 over R2 plus V3 over R3. Now we can represent, like we can write our Vout voltage in terms of input voltages, because we know VA and we know that VA is the voltage across the positive terminal. That's going to be equivalent to voltage across the negative terminal. Voltage across the negative terminal is equal to VB, and here we already derived the Vout voltage in terms of VB, and since VA is equal to VB, we can replace all of these things in terms of VB instead of VB. Okay, so we can write our final answer, VO, that's going to be equivalent to RT times V1 over R1 plus V2 over R2 plus V3 over R3 times, so this is this part, VB part, times RF over RI plus 1, and that's going to be the output voltage for a summing non-inverting amplifier. I hope this helps. Thanks for watching.